Hello, this is Mr. Koker. We're doing the homework for 1.B.2. These homeworks are found at the back of Chapter 8, starting with 8.52. It says arrange the following in order of increasing first ionization energy: fluorine, potassium, phosphorus, calcium, and neon. So I've arranged these in the order that I believe it should be, and I will try to justify why that is. I will start with potassium. The outermost electron in potassium is the fourth energy level 4s electron 4s1. The approximate Z effective for potassium, the approximate pull that it feels for the nucleus, is 1, and so it has a very weak pull for the nucleus, and it has a very large distance from the nucleus for its 4s electron, and so it will be the easiest to remove of the 5 atoms listed here. Calcium will be the second easiest. Its electron is also in the 4s like potassium, but calcium has one more effective nuclear charge because it has one more proton in the nucleus to pull the 4s electron in. Potassium has the third energy level for its valence shell, and it has an approximate Z effective of 5 with 15 protons and 10 first and second shell electrons to repel it. 15 minus 10 is 5. So with a Z effective of 5 and a third energy level, I will put it in the middle. I will say that the fluorine electron is very hard to remove, so it has a high ionization energy. It has a Z effective of approximately 7, has 9 protons and only 2 shielding electrons in the first energy level. Plus the fluorine electron that is being removed is in the second energy level, which is closer to the nucleus than the third or the fourth energy levels of potassium, calcium, and phosphorus. Finally, the most difficult to remove is neon because of its Z effective of 8. 10 protons, only 2 shielding electrons. The electron that's being removed is in the second energy level, similar to fluorine, but with 1 extra proton in the nucleus, neon will have the hardest to remove. 8.54 says, in general, ionization energy increases from left to right across a given period. Aluminum, however, has a lower ionization energy than magnesium. Explain. So we have talked about the sublevel effects as being one of the exceptions to the increase in ionization energy across a period. This particular sublevel effect is due to the difference in energy or the difference in shielding of the 3p electron, which is the one being removed from aluminum, and the 3s electron, which is the one being removed from magnesium. So the graphs that I handed out about the penetration effect show that the 3s has more penetration closer to the nucleus than the 3p, which both lowers the energy of the 3s and makes it harder to remove, and shields the 3p and makes it easier to remove. And so the 3p electron has a lower ionization energy than the 3s, despite the increase in nuclear charge that you see going from magnesium to aluminum. Okay, now we have 8.56. It says 2 atoms have the electron configuration 1s2, 2s2, 2p6, and 1s2, 2s2, 2p6, 3s1. Now those atoms would have to be neon and sodium. The first ionization energy of one is 2080 kilojoules per mole, and that of the other is 496 kilojoules per mole. Match each ionization energy with one of the given electron configurations and justify your choice. So I decided to match up the higher ionization energy of 2080 with neon and the lower ionization energy 496 with sodium. And I did so because the electron being removed from sodium is a 3s electron in the third energy level, which is well shielded by the first 10 electrons, the 1s2, 2s2, 2p6 shells. And so the core electrons in sodium shield the 3s well, and the distance of the 3s is farther from the nucleus. So it is easier to remove. In the case of neon, 1s2, 2s2, 2p6, the electron being removed is from the second energy level, which is only very well shielded by the first energy level, which is only 2 electrons. And so with a nuclear charge of 10 for neon and 2 shielding electrons, you have an effective nuclear charge of approximately 8, and the distance of that electron in the 2p is going to be farther from the nucleus. So it's easier to remove an electron from sodium than it is from neon. So sodium would be the lower ionization energy of the two. Okay, let's take a look at 8.58. We're supposed to use the equation from 8.57. So 8.58 reads, plasma is a state of matter consisting of positive gaseous ions and electrons. In the plasma state, a mercury atom could be stripped of its 80 electrons and therefore would exist as Hg80+. Use the equation in problem 8.57, which is this equation here. Energy level N is 2.18 times 10 to the minus 18 joules times Z squared divided by N squared. To calculate the energy required for the last ionization step, that is to go from mercury 79 plus to mercury 80 plus, to remove the very last electron mercury has. So you've stripped off 79 electrons, now you're going to strip off the 80th and final electron of mercury. Now the energy level equation gives us also the energy needed by changing the sign to ionize that electron off of the atom, because we want to bring it up to the energy level infinity, which is 0. And so whatever negative energy the energy level has, that's how much positive energy you put in to get the energy of the electron up to the point where it's out of the atom. So plugging in our numbers, the only number we need to plug in is Z and N. Well, Z would be the nuclear charge, which is 80. So 80 squared for Z squared. And N, the electron, the 80th electron removed from mercury, would come from the first energy level because you've stripped away all the other electrons. So the last electron removed would be from the first energy level, so N equals 1. When I do the math on that, I get 1.3952 times 10 to the minus 14 joules per electron. But looking in the back of the book, they report the answer in kilojoules per mole, which is fairly standard. So a quick conversion, 1 kilojoule is 1,000 joules. So divide by 1,000 to get it joules to kilojoules, and then multiply by Avogadro's number to convert from electrons to moles of electrons, because we're going to remove a mole of electrons from a mole of mercury 79 plus ions. So when that work is done, we end up with 8401894.4 kilojoules per mole, which in scientific notation would be 8.40 times 10 to the 6th kilojoules per mole. I think the back of the book said 8.43, so there must be a difference in some of our rounding. So we're going to try the last problem now, 8.100. It says a technique called photoelectron spectroscopy is used to measure the ionization energy of atoms. We've talked about PES in class and done a homework on it. A sample is irradiated with UV light and electrons are ejected from the valence shell. The kinetic energies of the ejected electrons are measured. Because the energy of the UV photon and the kinetic energy of the ejected electron are known, we can write that H times nu, the energy of the photon, is equal to the ionization energy, the amount of that energy needed to remove the electron, plus 1/2 mu squared, the kinetic energy left over in the electron's kinetic energy. So the symbol nu, looks like a V, but it's a nu, is the frequency of the ultraviolet light, and m and u are the mass and the velocity of the electron respectively. In one experiment, the kinetic energy of the ejected electron from potassium is found to be 5.34 times 10 to the minus 19 joules, using a UV wave source of 162 nanometers. Calculate the ionization energy of potassium. How can you be sure that this ionization energy corresponds to the electron in the valence shell? That is the most loosely held electron. Okay, so here is our equation. H nu equals IE plus 1/2 mu squared. We are replacing the 1/2 mu squared, which is the kinetic energy of the electron, with 5.34 times 10 to the minus 19 joules. Then we are replacing H nu with the Planck's constant H and the frequency nu. Now we're going to have to go down below in this little squared off area and calculate the frequency based off of the wavelength. So this uses a couple equations that we learned about in Chem 1. One equation in particular, C equals lambda nu. 162 nanometers would be the same as 1.62 times 10 to the minus 7 meters. And the speed of light is 3 times 10 to the 8th meters per second. So 3 times 10 to the 8th divided by 1.62 times 10 to the minus 7 gives us a frequency of 1.85 times 10 to the 15th cycles per second. In other words, the light cycles that many times per second. Plugging that back up in the H times nu, we get 6.626 times 10 to the minus 34 joule seconds, Planck's constant, times nu, 1.85 times 10 to the 15th joule seconds. The seconds cancel out and we end up with joules. So we end up with 1.22 times 10 to the minus 18 joules. Subtracting from that the amount of that energy that ends up as kinetic energy of the electron. So subtracting 5.34 times 10 to the minus 19 joules, we get 6.9 times 10 to the minus 19 joules. But when we check the back of the book, they have it in kilojoules per mole. So that means we need to do the conversion of joules to kilojoules and electrons to moles. So we do that conversion and we get 417 kilojoules per mole, which is pretty close to what the back of the book had, which I believe was 418 kilojoules per mole. Now how can I be sure that this is the electron in the fourth energy level, the easiest to remove? Well, this would be, if that were true, then we would be looking at the most energetic kinetic energy electrons. So if we've measured, in fact, the electrons with the greatest amount of kinetic energy, then we have found the electron which is easiest to remove, because the smaller the ionization energy, the greater amount of leftover kinetic energy the electron will have.